Hello everyone, I hope you are all enjoying PIMRC and thank you for attending this presentation. Let's begin. This presentation summarizes joint work with Elena Manole, which was carried out at Lancaster University. Unmanned aerial vehicles, referred to as drones, are considered for many applications, including wireless communications. Drones, serving as either flying base stations or relays, have the potential to enable future services. We focus on relay drones, which can be used to connect network nodes when the line of sight channel is blocked. Relay drones are not always required to establish an end-to-end communication path between two nodes. They can be dispatched from multiple bases to a field site with the objective of collecting information transmitted by an on-site data gathering source node. The collected information is stored on the drones, which carry and deliver it to their designated bases for further processing. In this work, we assume that a drone cannot provide feedback to the source node, and we derive two probabilities. The probability that a specific base will fully recover the broadcast information, or just a fraction of the broadcast information, and the probability that all of the bases will fully recover the broadcast information. In this investigation, two methods are studied: the data carousel method and random linear network coding. To briefly explain each method, let's assume that the source node has 5 data packets from packet 1 to packet 5 and is allowed to make up to 12 packet transmissions. When the data carousel method is used, the sequence of the 12 broadcast packets will consist of the 5 data packets, followed by another copy of the 5 data packets, followed by packets 1 and 2. When random linear coding is used, the sequence of the 12 broadcast packets will contain the 5 data packets, followed by 7 encoded packets now, which are random linear combinations of the data packets. We consider a source node S, which has a message for n bases B1 to Bn. A base Bi sends Li drones to receive the message and deliver it back to the base. In this example, base B1 will send 2 drones, so L1 is equal to 2. The drones dispatched by a base Bi form a cluster Ci as shown in the animation. The message at the source node is segmented into k data packets, which we shall refer to as source packets. As mentioned before, the data carousel method and random linear network coding, or RLNC for brevity, will be used in the broadcast phase. The source node generates NT packets from the k source packets and broadcasts them over packet erasure channels. The packet erasure probability of the channel that connects the source node with drone J of cluster I is denoted by εij. Remember that feedback channels are not available. The drones of each cluster return to their respective bases and offload the packets that they have collected. Each base then attempts to reconstruct the source message. If the bases are isolated, they cannot exchange packets. If they are interconnected, they can share packets, increase diversity, and improve the chances that every base will obtain the source message. The mission is deemed a success if all of the n bases can recover the k source packets and thus reconstruct the source message. We shall now focus on the case of isolated bases when the data carousel method is employed. According to this method, the source packets are repeatedly transmitted until a target number nt is reached. In this example, the k source packets have been transmitted lambda times. Number nt is reached after the first row source packets are transmitted again. In other words, nt can be written as lambda times k plus rho. The nt transmitted packets can be divided into 2 blocks. The block on the left-hand side contains copies of the first row source packets, which have been transmitted lambda plus 1 times. The block on the right-hand side contains copies of the remaining k minus rho source packets, which have been transmitted lambda times. The probability that base BI will recover the k-source packets is a product of two terms associated with the two blocks. The first term is the probability that at least one of the lambda plus 1 transmitted copies of the first raw source packets will be received. The second term is the probability that at least one of the lambda transmitted copies of the last k minus raw source packets will be received. The quantity epsilon I is the probability that a cluster will fail to receive a packet, which will happen when every drone in that cluster fails to receive the packet. The mission success probability is the product of the probability that each of the n bases will recover the k source packets. Recall that when RLNC is used, we said that the k source packets are transmitted along with nt-k coded packets, so nt transmitted packets in total. For this reason, this type of RLNC is referred to as systematic RLNC. If n of the nt transmitted packets are offloaded at the base, the probability that the k source packets will be recovered has been derived in previous work of ours and is given by the expression displayed here. The expression considers that h out of the k transmitted source packets have been received, and the remaining k minus h source packets will be recovered from the nt minus k transmitted code packets, provided that k minus h linearly independent coded packets can be found among them. The expression is divided by the combinations of receiving any n out of the nt transmitted packets, and a sum is taken over all valid values of h. The probability that a base BI will reconstruct the source message considers the probability of recovering the k source packets when n packets have been received for every possible value of n. The probability of mission success is not given by the product of the probabilities that every base will recover the source message, because the coded packets that are deposited onto different bases introduce statistical correlation, as explained in a paper by Cimballo et al. However, the same authors proved that when systematic RLNC is used, this product is a lower bound on the desired probability and also a tight approximation. The probability of mission success will improve if each base can share acquired packets with every other base. Even if the full source message is reconstructed by the interconnected bases within an acceptable time frame, each base could have the additional requirement of recovering at least part of the message, that is, mu of the k source packets, as soon as the drones of the respective cluster offload the received packets. We can consider the case that a base will recover y1 of the first raw source packets and y2 of the last k minus raw source packets, derive the joint probability of acquiring y1 and y2 source packets, set y1 plus y2 equals y, and then calculate the probability of recovering at least mu source packets by letting y take values in the range from mu to k. To compute the probability of mission success, we can use the expression for the mission success of one base. This is because the group of n interconnected bases can be viewed as a single base, while the union of the n clusters can be treated as a single cluster of drones which offload received packets at the base, experiencing equivalent erasure probability epsilon. In a similar fashion, we can obtain expressions for the probability that a base will recover at least some of the source packets, as well as the mission success probability when systematic RLNC is used. Let us now review some of the results. In the first setup, the source node has 20 packets and uses a data carousel or systematic RLNC to broadcast NT packets where NT varies from 20 to 35. Transmission is over packet erasure channels. Two clusters containing 3 and 2 drones listen to the transmission, store successfully received packets, and return to their bases to offload them. The two bases are isolated. The red and blue curves show the probability of base 1 and base 2 respectively recovering the 20 source packets as a function of the transmitted packets. The black curve depicts the joint probability that both bases will recover the source packets and hence the source message, which represents the mission success probability. When systematic RLNC over finite fields of only 2 elements is used, the probability of message recovery improves significantly. And increasing the size of the finite field from 2 to 8 can further improve the mission success probability for a given number of transmitted packets or reduce the required number of transmitted packets for a target probability of message recovery. If the two bases are interconnected and can exchange packets, the probability of mission success improves markedly. However, the exchange of information between bases may take time, and a base may need to recover as much of the transmitted source message as possible, as soon as possible. The purple line shows the probability that at least 90% of the message, that is 18 of the 20 source packets, will be recovered by base B1, while the red line shows the probability of recovering 95% of the message. As before, systematic RLNC can boost the probability of message recovery, but an interesting observation can be made when the field size increases from 2 to 8. Let us focus on the red lines, which depict the probability that base B1 will reconstruct at least 95% of the message, and zoom in. We see that an increase in the field size from 2 to 8 reduces the probability of partial message recovery. The benefit of using a larger field size is seen only when the number of transmitted packets exceeds a value, which is 23 in this case. When a single base is required to collect data from a remote source node, which needs to keep packet transmissions as low as possible due to energy or time constraints, the optimal number of dispatched drones depends on the expected packet erasure probability and the chosen transmission method. The impact of the number of drones on the number of transmitted packets when the target probability of mission success is 99% is illustrated in this figure. For a given erasure probability, we observe that there is a minimum value of drones for which the number of transmitted packets becomes equal to the number of source packets, which has been set to 30. For instance, when the erasure probability is 0.4, no more than 9 drones are required to reduce the number of transmitted packets to 30. Furthermore, if 9 drones are dispatched, the simple data carousel can be used. The additional encoding and decoding complexity introduced by systematic RLNC can be justified when the available drones are 8 or fewer, as the value of the required transmitted packets does not increase as sharply as in the case of the data carousel. To conclude, we presented a theoretical framework for deriving the probability that a base will retrieve some or all of the source packets and the probability that all of the bases will fully reconstruct the source message. Results demonstrated that systematic RLNC over large fields is a good choice if our objective is to fully recover the source message. However, if it is essential to recover even a large fraction of the message, we should consider using systematic RLNC over small fields. Last but not least, the simpler data carousel method could match the performance of RLNC if you can afford a larger number of drones. Thank you for listening. For more details, please refer to our paper. Thanks again.